Good day, everyone. As I start this video, I'm still on spring break, but we want to hit the ground running when we come back from spring break because we have an exam that week. Although, admittedly, this new worksheet I have here is on chapter 21, which is not on exam 3. That will be on exam 4. But chapter 21 is a critically important chapter, and it has to do with nucleophilic acyl substitution. So in all the reactions that we're learning in chapter 21, they all follow that pattern. They all involve some acyl derivative, some carboxylic acid derivative, in which the leaving group attached to the carbonyl will be replaced with something else. And I can't think of a single counterexample in the chapter. So I've just prepared this new worksheet for you. It will be ready for use with studying for chapter 21. And of course, as always, we have the practice exams. Just a reminder, the practice exams, there are 4 practice exams, even though we have 5 exams. So you need to remember that the chapters are spread out a little bit differently on those 4 practice exams than are in our 5 exams. So as always, take a look at the practice exam videos. If you see any questions in the practice exam video that are not on the practice exam you're looking at, then they most likely belong to another chapter. And you'll find them covered either for the previous exam or for the next exam. So that would be my advice. So first, I've chosen some questions from a past exam that involve filling in the reagents given the starting material in the product. So in this first reaction, we're converting benzoyl chloride to methyl benzoate. So we're converting an acid chloride into an ester. And there are a couple ways to do that, at least 2 ways that I can think of. One of them, I'll just write the reagents down here. One of them would be under acidic conditions. We clearly need to use something with a CH3O group, right? Because we need to replace the Cl with CH3O. So we need something with a methoxy group in it. And the most readily available compound with a methoxy group in it that can be transferred elsewhere is methanol. And then remember, in acid solution, you will also have the conjugate acid of the alcohol. And this could, of course, also be done under alkaline conditions. You could also use, let us say, sodium methoxide. So either of those sets of reagents would be perfectly acceptable. And there's more than one correct way to write them, but I think that's the most concise and consistent way of doing it. In the next reaction, we're given carboxylic acid. This one happens to be propionic acid, and a secondary amine. This happens to be called pyrrolidine, and the product is an amide in which the nitrogen of the amine replaces the OH group of the carboxylic acid. And we're clearly going to lose a molecule of water in the process. We lose the OH and the H on the nitrogen. And so we bring those 2 groups together. And we talked about a reagent that we're going to get to again when we get to chapter 26, which is on polypeptides, because this is a reagent that's constantly used in that field in order to prepare polypeptides in the lab. And that reagent is called dicyclohexyl carbodiimide, or DCC. And you can find the structure of that compound and of the byproduct to the reaction, which is the dicyclohexyl derivative of urea. And so please be sure you learn those structures. I don't want you just memorizing letters, but always be aware of what reagents you're using. So DCC is the reagent of choice. You don't need to put anything else. That's the reagent of choice. In the pharmaceuticals, or really I should say in the industry in which they make polypeptides, I don't believe there is a solvent that's used. It's all done on a solid phase. And to my understanding, it's all done strictly computer controlled and has been for decades. So dicyclohexyl carbodiamide is the preferred reagent. Since we have some time here, I'll just remind you of what the structure of dicyclohexyl carbodiamide looks like. It has a very peculiar structure. Well, I don't really want to do that. Let's move it down here. And dicyclohexyl carbodiamide looks very much like CO2, actually, except that instead of oxygens, we have nitrogens. And so the central carbon is sp hybridized, just like in CO2. Those nitrogens would have to be sp2 hybridized to accommodate the double bonds. And they, of course, would be ordinary nitrogens that obey the octet rule, as always, with lone pairs on them. So that's the structure of DCC. Good. So, so much for these problems. Next, we have some problems where we can practice filling in the product. And so the first one involves treating an acid chloride with an amine. Don't get distracted by the oxygen in the, oh, I'm blanking on what that molecule is called. I don't really care if you guys know it, but these molecules do have names. Morpholine, that's what that compound's called. And so we're treating the acid chloride with the nitrogen of the morpholine. The way you know that is because the nitrogen is an H on it that can be removed. That nitrogen can be deprotonated, and that will happen during the course of the reaction. The other species we're given is the conjugate acid of morpholine. There's an extra H on the nitrogen, and the nitrogen has a plus charge. So you're given an acid chloride, you're given an amine, and you're given the conjugate acid of the amine. These are typical reagents for an aminolysis of an acid chloride. So we'll write that down over here. And again, you can tell that from the reagents that were given. So what we're going to do is replace the chlorine on the acid chloride with the nitrogen of the amine. This is going to go with the net loss of HCl, but we'll just attach this nitrogen directly to the carbonyl carbon. And so if I were to draw this, we would take away the chlorine. That's now going to have a six-membered ring attached to it. The nitrogen of the morpholine is going to be attached to the carbonyl carbon, so you get an amide. And of course, the oxygen at the other side of the six-membered ring is just along for the ride. That's still there. So that would be the structure of the major organic product. You'd get this amide from the acid chloride. This is aminolysis of an acid chloride. The oxygen does nothing. It's just along for the ride. And in the next reaction, we have an ester that we're treating with an excess of a Grignard reagent. And we covered this reaction in class. This is treatment of an ester with excess Grignard reagent. And the product is going to be a tertiary alcohol. One equivalent of the Grignard reagent, in this case methyl Grignard, will attack the carbonyl carbon, and you'll get a tetrahedral intermediate with O- over here. And then the electrons on the oxygen fold back in to reform the carbonyl and kick out the ethoxide ion, which is perfectly fine because we're in alkaline solution. The way you know that is that Grignard reagents are very strong bases. We learned that in chapter 10 of the first semester. So the first species you get is the methyl ketone. And then ketones, of course, still react with Grignard reagents. We learned about that in chapter 19. So the methyl Grignard will add again, and you'll get a tetrahedral intermediate with O- over here. And then the O- will pick up a proton from the acidic workup and make OH. So you wind up with a tertiary alcohol. We can move most of that structure over here. And so you'll get a tertiary alcohol with two methyl groups. There's your alcohol functional group. And this whole, well, certainly that methyl group, I don't know if I can turn it red like that. No, I guess not. That's it. I have to select the bond. And so those two methyl groups both came from the Grignard reagent. The ethoxy group in the ethyl ester will wind up in a molecule of ethanol. Ethanol is soluble in water in all proportions. So during the acidic or during the aqueous workup, when you dump everything into a separatory funnel and do an organic aqueous extraction, the ethanol will wind up in the aqueous layer and thus go to the waste jug. The major organic product will be this tertiary alcohol. So when you treat an ester, or for that matter, an acid chloride with excess Grignard reagent, you will wind up with a tertiary alcohol. The book points that out about acid chlorides, but really doing this, no one ever really does this reaction with an acid chloride. They'll want to use an ester. Esters are much easier to handle than acid chlorides. They're much less reactive, so they stand up to the reaction conditions without hydrolyzing. And so methyl or ethyl esters of this type are very readily available, at least as much so as acid chlorides, if not more so. And so the product will be a tertiary alcohol resulting from addition of two equivalents of the Grignard reagent. So much for those problems. We've dispatched those. We've got a few more over here. In this reaction, we're taking phenylacetonitrile and we're heating it up in aqueous acid. Remember, whenever you're given H3O+, H2O is always there also, whether or not it specifically mentions it. Again, you can't have a bottle of H3O+. H3O+ is dilute aqueous acid. And the way you make it is by taking water and adding a little bit of some really strong acid, like sulfuric acid or maybe phosphoric acid. Phosphoric acid isn't quite as strong as sulfuric acid, but it would do the job. You just need a little bit of some acid catalyst. Paratoluene sulfonic acid, TSOH, is also fine, and that's something that Active is very fond of. They use it all the time, as you've noticed in your online homework. But any of those can just generically be referred to as H3O+. H3O+ means that you've got H2O with some H3O+ ions floating around in it. And under these conditions, with heat, you're going to hydrolyze the nitrile. So this is acid hydrolysis of nitrile. And that's a reaction that we'll cover in chapter 21 at the end of the chapter. And the product that you get is the corresponding carboxylic acid. The nitrogen winds up in a molecule of ammonia, or to be more precise, in an ammonium ion, NH4+, and the oxygen and the OH both come from water molecules. So you get the corresponding carboxylic acid. Be sure to count your carbons. Notice that our product has the same number of carbons as the starting material. So the carbon that's now involved in the carbonyl was the nitrile carbon. And again, the nitrogen of the nitrile winds up in an ammonium cation. In the next reaction, we're treating a carboxylic acid with thionyl chloride. And this is a reaction also that we've covered, formation of an acid chloride from a carboxylic acid. And thionyl chloride is the reagent of choice. You're not responsible for the mechanism of this reaction, but you need to be aware that it essentially turns the OH group into a chlorine. You just get the corresponding carboxylic acid. And then finally, we've got a carboxylic acid upon treatment with LAH in an ether solvent, in this case diethyl ether. THF would also be fine, of course, followed by an aqueous acid workup. So this is LAH reduction of carboxylic acid. And the product that you get from that is a primary alcohol. You learned about that reaction first in chapter 17, but we reviewed that here in chapter 21. And so the product that you get will just be this, the corresponding primary alcohol. The effect of the LAH followed by the acid workup is to reduce the carbonyl of the carboxylic acid all the way down to a CH2. And both of those new hydrogens that are on the carbon attached to the alcohol, both of those hydrogens come from LAH. So yeah, that's pretty much it for these problems. And with that, I think we'll shut down ChemDraw and just go straight to MS Word. We have a couple of mechanisms here. And so in the first one, we're going from this methyl ester to the carboxylic acid. Always when you're given a mechanism, look carefully for what changes over the course of the reaction. And you can see we're going from OCH3 to OH, and everything else stays the same. So we are hydrolyzing that methyl ester. Could have been any other kind of ester as well, and you will get the corresponding carboxylic acid. And then in the next mechanism, we're going from this carboxylic acid to now a propyl ester, and we're given propanol and the conjugate acid of propanol. So this is nothing more than a Fischer esterification. So you've got acid hydrolysis of an ester followed by Fischer esterification. These reactions are essentially opposites of each other. And then don't forget, in chapter 21, we've also got nucleophilic acyl substitution reactions that involve amines. So we spoke about aminolysis reactions. Those mechanisms are very much the same. They just use an amine instead of an alcohol. And then we also talked about other reactions, such as conjugate additions to alpha-beta unsaturated species. So be sure you learn those mechanisms as well. And we have some of those mechanisms on the practice exams. So these are both nucleophilic acyl substitution reactions. The first mechanism in which we go from methyl salicylate to salicylic acid is in aqueous acid medium. And remember, we've made this very clear in class. When you're in acidic medium and there's a reaction that involves nucleophilic addition to a carbonyl carbon, the first step will always be protonation of that carbonyl oxygen using whatever acid you're given. And in this case, the acid we're given is H3O+. So we draw an H3O+ ion, we highlight one of the oxygen-hydrogen bonds, and we use one of the lone pairs on the ester carbonyl oxygen to pull off a proton from the hydronium ion and give us this intermediate. So that's the P of the PAD-PAD. Then comes the A of the PAD-PAD that I've ruthlessly stolen from Dr. Serrano-Lugo. By the way, I've already spoken to her. We have her full permission. And so now comes the A of the PAD-PAD. A can stand for either addition or attack. You can look at it either way. But now, whatever you're given that is the most nucleophilic species is going to attack that carbonyl carbon. And in this case, our most nucleophilic species is water. Of course, we can't have hydroxide ions in acidic medium. In alkaline medium, yes, but not in acidic medium. So we show a water molecule attacking that carbonyl carbon, breaking the carbon-oxygen pi bond, putting the electrons on the positively charged oxygen, and giving us now this tetrahedral intermediate. Now's the time for some proton transfers and the D and the P of the PAD-PED. So the D comes first. We have deprotonation, and the way you know what to deprotonate is by finding whatever atom has a plus charge on it. That's the atom you will want to deprotonate. There should be one. There will always be one. And in order to do the deprotonation, what you use as a base is whatever you're given that's the most alkaline species. And in aqueous acid, the most alkaline species is water. So we use a water molecule to pull the proton off of that OH group. And again, if this were some kind of alcoholysis reaction, then it would be the alcohol that we'd use as a base. If this were an aminolysis type reaction, we'd use the amine we're given as a base, whether it's a primary or secondary amine. So we pull that proton off. That gets us to an intermediate with zero charge. So that's the D of the PAD-PED that we just did. Now we have the next P of the PAD-PED, the next protonation. And so you need to protonate now whichever atom you wish to eliminate. And we can tell by looking at the structure of the product that we need to get rid of the CH3O group. We need to lose it as a molecule of methanol. We can't lose CH3O minus here, not in acidic solution. That's too strongly alkaline. If we were in alkaline solution, we could lose the methoxide ion as a leaving group. That would be fine, but not in acidic medium. In acidic medium, now comes the P, and we have to protonate that oxygen first. So as your acid, you just use whatever you're given. Always look back at what you're given and use whatever species is the most acidic. In this case, it's H3O plus, just like it was for the first step. So we draw out a hydronium ion. We especially draw out the hydrogen-oxygen bond. We show a lone pair from the methoxyoxygen, picking off a proton from the hydronium ion, and we get this intermediate. So we've had PADP of the PAD-PED. Now comes the E. The E stands for elimination. And you will now eliminate a molecule, whichever molecule can act as a leaving group, and is, again, I think you'll find, going to involve an atom with a plus charge. If you've done it right, you'll have an atom with a plus charge here. And that's going to be the molecule that you'll eliminate. So we break the carbon-oxygen bond between the central carbon and the methanol molecule, and we release a molecule of methanol as a leaving group. And then we can and should also take a lone pair from one of these OH oxygens. It doesn't matter which, they're the same. So we show a lone pair from one of those oxygens coming in between the carbon and oxygen and making a pi bond. And that gets us to this intermediate. This is nothing more than our carboxylic acid product with an extra proton. So finally comes the second D of PAD-PED, another deprotonation. We need to deprotonate this atom because it has a plus charge. That's how we know we need to do it, because we have an atom with a plus charge. So we need to do a deprotonation to get rid of the plus charge. We saw that in chapter 19, and we see that again in chapter 21. So go back again and look at what you're given and pick whichever species is the most alkaline. And I think you'll all agree water is much more alkaline than the hydronium ion. So we'll use a water molecule. We'll use more specifically one of the lone pairs on the water molecule oxygen to form a bond to this hydrogen and break the oxygen-hydrogen bond, which gives us our neutral product, the carboxylic acid. So this is, again, acid hydrolysis of an ester. That's a reaction we covered from chapter 21. Next, we've got a Fischer esterification, which is essentially the exact opposite reaction, and it includes the same steps, but in the reverse order. So we've got, again, a reaction that's in acidic medium. We know that because we're given an alcohol and its conjugate acid. Remember, if you're given a cation that's not a metal cation, chances are very high that you're in acidic medium. I can't think really what else would cause you to be given that. So we know we're in acidic medium, and also we're looking at a reaction in which we expect there to be a nucleophilic attack on that carbonyl oxygen. That's a sign that we need to protonate the carbonyl oxygen first. If we didn't protonate the carbonyl oxygen first and just had a nucleophile attack this carbonyl carbon, well, then we'd wind up with an intermediate that had O-, an alkoxide ion. And that's no good in acidic medium. That's fine in alkaline medium, but not in acidic medium. Such a species is much too strongly alkaline to exist in acidic medium. So we need to protonate that oxygen first. It's again the first P of the PADPED. We've got another proton transfer, specifically a protonation. So how do we know what to put down to use as the acid? We look back at what we're given and we pick whichever species is the most acidic. And that's going to be the conjugate acid of the alcohol. So we'll draw out that molecule. Notice again, I'm showing the OH bond because we need to show that bond being broken. Our carboxylic acid will reach out with a lone pair from the carbonyl oxygen and use that to pull off a proton from this acid. We break the hydrogen-oxygen bond, and that gets us to this protonated intermediate. So now we're ready for the nucleophilic attack. That's the A of PADPED. You can think of it as either attack or addition. Both will work. Both are perfectly correct. And so the way you know what to show adding to that carbonyl is again by looking at what you're given and picking whichever species is the most nucleophilic. And that's going to be the alcohol. So we show the alcohol with one of its lone pairs in oxygen attacking that carbonyl carbon. We break the carbon-oxygen pi bond as always and put the electrons onto the oxygen nucleus and get rid of the plus charge. Notice I'm showing a neutral free alcohol here. I'm not showing O-. Drawing this with O- instead of OH will lose points. That's incorrect. We can't have any of this alkoxide in acidic medium. There wouldn't be any in an acidic medium. In an alkaline medium, maybe we might have some, but not an acidic medium. That species is too strongly alkaline. So we use the alcohol, not the alkoxide. That gets us to this intermediate, and now we're ready for the D and the P. We're ready for a deprotonation followed by a protonation. So we first need to deprotonate whatever atom has the plus charge. That's how you know which atom to deprotonate. There should be an atom with a plus charge, and in order to get rid of the plus charge, we deprotonate that atom. Now, how do we know what to use to deprotonate that atom? This is where, the reason I keep stressing this is I think a lot of students memorize H2O goes here. No, it's not always H2O. If we were in an aqueous medium, it would be, but we're not in an aqueous medium. You'll notice no H2O is mentioned in what we're given. The only protic species we have that can act as a base is going to be this alcohol. And so that's what we'll use as our base to pull the proton off the oxygen with a plus charge. That gets us this neutral intermediate. And then after our deprotonation, that's the D, we have a protonation, which is another P. And again, for a protonation, just exactly like we did before, we'll use the exact same species. We'll use the conjugate acid of the alcohol that we're given. We just copy that down from the species that we're given. We draw out the OH bond, and we then proceed to protonate either of these two OH groups. It doesn't matter which, they're the same. So we show a lone pair on one of the OH groups, pulling off a proton from this protonated alcohol, the conjugate acid of the alcohol. We break the oxygen-hydrogen bond and release a neutral alcohol molecule. And that gives us this intermediate. So we got PADP, now comes E for elimination. And we're now ready to eliminate a molecule of water. So we show the CO bond breaking with the electrons going onto the positively charged oxygen, and we lose a molecule of water. And then one of the lone pairs on the OH group will help to push out the water molecule by donating inward one of its lone pairs to make a carbon-oxygen pi bond. That gives us this intermediate. And that's almost our ester. There's just this extra proton that we have to get rid of. So we need to find a base that can pull this proton off for us. Once again, just like we found over here in this step, the base is going to be the alcohol that we're given. If this were some kind of aminolysis reaction, the base would be the amine that we're given. But whatever it is that we're given, that's what we'll use. That will pull off the proton from the positively charged oxygen. We break the oxygen-hydrogen bond. The electron flow is as you see here, and we get our ester. So these are both very typical nucleophilic acyl substitution reactions with mechanisms that are worth your studying. And that's about it. With that, we're done with this worksheet. And so, yes, so as I said, it's going to be a few more days until I see you all on Monday. I hope you're all enjoying your spring break, and I will look forward to seeing you then. Have a great day.